In this example, R22 is the system refrigerant running through the evaporator, which is absorbing heat from an interior zone. In this instance, the thermostatic charge is also R22. The spring pressure is set by the manufacturer to be 12 psi gauge, and the evaporator operates at 52 psi gauge. Therefore, in order to open the valve, a downward force greater than 64 psi gauge is required by the sensing bulb. At 52 psi, the evaporator's saturation temperature is approximately 28 degrees Fahrenheit. The temperature measured at the sensing bulb is 37 degrees Fahrenheit. Since the thermostatic charge is also R22, the same table is used to determine the bulb pressure. When the sensing bulb is exposed to 37 degrees, the pressure exerted on the diaphragm is approximately 64 psi gauge. The valve diaphragm is experiencing a 64 psi opening force from the bulb and a 52 plus 12 psi closing force from the evaporator and spring. The valve is balanced because both sides exert a 64 psi force. Superheat is determined by taking the difference between the sensed bulb temperature and the evaporator saturation temperature. Subtracting 37 degrees from 28 degrees gives a superheat of 9 degrees for this cycle. What would happen if the outlet temperature decreased from 37 degrees Fahrenheit to 35 degrees Fahrenheit? To start, let's remind ourselves how the cycle should respond if a change in cooling load causes the superheat to decrease. When the cycle's superheat decreases, liquid refrigerant is traveling further in the evaporator. Point A is now moving closer to the sensing bulb. Instead of heating the refrigerant up to 37 degrees, we are only heating up to 35 degrees, which means we are approaching the saturation region on the pressure enthalpy diagram. This is actually a sign that we have too much refrigerant in the evaporator. In order to restore the desired superheat, the flow rate to the evaporator needs to decrease. With less refrigerant in the evaporator, more of the heat extracted from the indoors will be available to increase the refrigerant temperature back to 37 degrees. Since the bulb temperature decreased, we should expect to see the expansion valve respond by closing in order to decrease refrigerant flow. Let's see if that's what happens. When the sensing bulb experiences a temperature of 35 degrees, the bulb pressure becomes 61.5 psi. The drop in bulb pressure means that now the 64 psi closing force exerted by the spring and evaporator is greater than the 61.5 psi opening force exerted by the bulb. This closes the valve, reducing refrigerant flow to the evaporator and increasing the superheat back to 37 degrees, exactly how we predicted the valve should respond. For this third example, it's your turn to test your understanding. In this example, the bulb temperature has increased to 38 degrees. The evaporator pressure and spring pressure remain constant. Determine the new bulb pressure and identify how the valve responds. Go ahead and pause the presentation and continue when you think you have the correct answer. The sensing bulb temperature increased to 38 degrees. Thus, the corresponding bulb pressure is 65.7 psi. Now the bulb pressure exceeds the 64 psi closing pressures. The valve begins to open. The thermostatic expansion valve is therefore controlling the refrigerant flow to maintain a constant 37 degree discharge temperature when the evaporator's operating pressure is 52 psi gauge. In all three examples, the valve responds until the refrigerant flow rate balances the desired superheat. Now, I mentioned before, the evaporator operating pressure depends on a number of factors and is not constant. What happens if the cycle operates at a different pressure? Let's look at an extreme case when the evaporator pressure rises to 70 psi. From the table, an operating pressure of 70 psi corresponds to a saturation temperature in the evaporator of 41 degrees. The pressures opening the valve are now 70 psi from the evaporator and 12 psi from the spring. A bulb pressure greater than 82 psi is required in order to open the valve. The sensing bulb will exert an 82 psi closing force when the sensing bulb temperature reaches 49 degrees Fahrenheit. The superheat at this point is the difference between 49 degrees and 41 degrees. Even at this new operating pressure, the superheat remained relatively constant, and that will be the case across the typical operating range of evaporator pressures these systems operate at. You can try similar examples yourself using different operating pressures. You'll find that the spring pressure set in the thermostatic expansion valve creates a near constant superheat temperature that is controlled independent of the load or operating pressure in the evaporator. This is an entirely mechanical control, which still requires calibration, but is not dependent on electricity or control signals. The evaporator's operating pressure may be connected to the thermostatic expansion valve at the evaporator inlet, known as internal equalization, or the evaporator's outlet, known as external equalization. Internal equalization is sufficient for smaller systems. However, larger evaporators will have higher internal pressure drops between the evaporator inlet and outlet. As an example, the schematic on the bottom shows the evaporator inlet has a pressure of 58 psi, but the outlet operates at 52 psi. In this case, the evaporator pressure exerted on the valve diaphragm is taken from the evaporator outlet. This is required in order to accurately control superheat without dependence on the fluctuating evaporator pressure drop. The benefit of the thermostatic expansion valve is the ability to maintain constant superheat irrespective of evaporator pressure or cooling load. However, the sensing bulb thermostatic expansion valve is only one of many throttling devices used in the refrigeration cycle. The thermoelectric expansion valve, automatic expansion valve, and capillary tube are all examples of other devices employed. Discussing all of these is outside the scope of this course, but we have presented one of the more common to give you a better understanding of the internal controls. There you have it. You now understand the basics of the refrigeration cycle, as well as how the thermostatic expansion valve modulates flow rate to respond to load. Now that we have discussed, in excruciating detail, how the refrigeration cycle is controlled internally, let's look at some typical direct expansion cooling applications you likely have on your installation. The simplest system is a single zone package unit or split system. This design is typical in residential homes and department stores. Cooling is provided by the refrigeration cycle DX unit, which is controlled based upon the zone temperature using two-position control. When the zone temperature rises above set point, the controller sends an on signal to the DX unit's control panel. From there, the unit could close a relay to energize the compressor and start the refrigeration cycle. Air passes over the evaporator, and the air supplied to the zone is cooled. Once the zone temperature is cooled below the control differential, the controller sends an off signal to the unit, which opens an internal relay and stops the refrigeration cycle. A multi-zone constant air volume system works very similar. The one difference is the refrigeration cycle is controlled based upon discharge air temperature. If the discharge air temperature exceeds 55 degrees, the controller will send a signal to the relay, which activates the refrigeration cycle. In this example, discharge air is maintained around 55 degrees with reheat available at each zone. This allows cooling to be delivered to zone 2, heating to be delivered to zone 1, and ventilation to be supplied to zone 3 without heating or cooling. If the mixed air temperature entering the air handling unit is less than 55, it would be increased by the heating coil. If you understand the control of these two designs, you understand how all DX systems are controlled. Either they are controlled based upon the zone temperature or the discharge air temperature. In a dual duct design, the refrigeration cycle is controlled based upon the discharge air temperature of the cold deck. Thermal comfort is achieved by mixing the two air streams at the zone. The same control is used for multi-zone constant air volume with bypass. The DX unit is controlled based upon discharge air temperature. Unneeded heating or cooling is bypassed around the zone. When it comes to variable air volume systems, The control is exactly the same as multi-zone constant air volume systems. The DX unit cycles based upon discharge air temperature. This is true for cooling only VAV systems, shown here, or VAV cooling with zone reheat. There is one potential problem that may arise with VAV systems that you should be aware of. DX units have minimum face velocity requirements. If the velocity falls below this specification, moisture that condenses on the evaporator won't trickle down into the condensate pan as quickly. Additionally, less airflow means less heat to be removed from the airstream, and the evaporator's temperature may drop too low. These two issues are a recipe for ice to form on the evaporator. So if you install a split system or heat pump on a VAV design, you need to make sure the design minimum airflow never creates a situation where you fall below the minimum face velocity required at the evaporator. The last topic we will discuss in this lesson is various controls available to handle part load operation. Most residential DX units are two-position control. They are either on or off. The expansion valve regulates the flow of refrigerant to meet the cooling load as we just discussed. But the expansion valve is limited in how much it can modulate the unit's cooling capacity. For instance, let's say you have a 10-ton DX unit, but only need half a ton of cooling during one of the shoulder seasons. A thermal expansion valve is not designed to modulate flow to 5% part load capacity. Other staging controls are necessary. An example of when this might be needed is apparent in our multi-zone CAV schematic. Let's say we are trying to create 55-degree discharge air. The unit installed was designed in order to take 80-degree mixed air and cool it down to 55 degrees. But what about on a relatively cool day when the mixed air temperature is only 57 degrees? If we were to run the DX unit at full speed, the air would cool down quickly, the unit would shut off, then the air temperature would rise, forcing the DX unit to turn on again. This causes short cycling, which is terrible for the equipment and burns the compressor out quicker. Therefore, many times DX units employ one or more of the following controls to meet part load conditions. The part load capacity controls we will discuss are multi-stage sequencing, hot gas bypass, hot gas reheat, as well as internal compressor controls such as slide valves used in screw compressors, turning vanes used in centrifugal compressors, and variable speed drives. You can think of all these part load capacity controls as optional add-ons that cost more but provide higher efficiencies at part load. Perhaps you've heard of two-stage compressors or have one installed at your home. Two-stage compressors have a low stage and a high stage, providing two different capacities. The low stage might be sized to handle 60% of the design capacity, and when the high stage turns on, the compressor provides the total capacity. The high stage only kicks on when the low stage can't maintain set point. Two-stage control is really a subset of on-off control, which requires two set points and two differentials. In HVAC systems, it's employed often enough that we give it a unique name. We refer to it as step control. Let's look at the example of a two-stage DX unit designed to supply 55-degree air. The low stage set point is 55 degrees with a differential of 2 degrees, meaning the low stage will turn off when discharge air is equal to 53 degrees. The high stage set point is 57 degrees with a differential of 3 degrees, meaning the high stage will turn off when discharge air is equal to 54 degrees. When the supply air temperature increases above 55 degrees, the first stage turns on. As the evaporator removes heat, the temperature decreases. When discharge temperature reaches 53 degrees, the low stage turns off. The discharge air temperature begins to climb. Once it hits 55, the low stage will turn on. If there isn't enough capacity, the discharge air temperature will continue to rise. When the discharge air temperature hits 57 degrees, the second stage will turn on to provide additional cooling. Assuming the unit was sized correctly, the discharge air temperature will begin to fall back to set point. When the discharge air temperature reaches 54 degrees, the high stage turns off. This step control can be used in terminal heat pumps like you might see in a hotel, as well as in commercially sized VAV and multi-zone CAV systems. Additionally, larger HVAC units may have multiple compressors, each with 2 stages. Step control can therefore be an effective way to modulate capacity by adding additional compressors and stages as necessary. Another effective part load design that you may have heard of is hot gas bypass. This requires installation of additional hot gas bypass valve as well as piping between the high side and low side of the cycle. There are 4 acceptable ways to install hot gas bypass, but the preferred method is shown here. After leaving the compressor, some of the discharge vapor is directed back toward the evaporator and connected between the expansion valve and the evaporator. This creates a false load on the evaporator. The evaporator still extracts heat from the indoors, but this design allows the DX unit to operate at lower part load values. Now you may be thinking, but wait, this is a waste of energy. What sense does it make to increase the pressure and send it right back to the evaporator? You are correct, this consumes more energy. But remember, we should only be using hot gas bypass at low load conditions. An analogy to this design would be driving your car in the city. Do you turn off your engine every time you hit a red light? I certainly hope not. Instead, you'll let it idle even though you are consuming fuel without moving. Turning your car on and off at every red light would wear out your engine quicker. The same is true for our compressor. If you want to know more specifics about hot gas bypass, a Train newsletter has been made available to you in the supplemental readings. Another design available is called hot gas reheat. Similar name, but a different purpose than hot gas bypass. In this design, after leaving the compressor, hot gas is routed to an additional heat exchanger placed downstream of the evaporator. This design is useful in cool, humid environments where humidity control is a concern, but the temperature of the air doesn't need to be cooled. As humid outdoor air passes over the main evaporator, moisture condenses out of the airstream and the temperature decreases. As the airstream passes over the reheat condenser, only the temperature is increased. Now the supply air distributed to the zones has significantly less humidity than the outdoor air, but the air temperature is only slightly lower. Compressors may also be installed with internal capacity control to more accurately meet load. For screw compressors, slide valves are used to allow inlet gas to bypass portions of the compressor, which results in different levels of compression. This video shows the slide valve moving to 4 different locations, allowing the compression ratio to be adjusted between 25 to 100% of design. Centrifugal compressors use inlet guide vanes to modulate capacity. These movable vanes adjust the direction of vapor entering the compressor. This changes the angular momentum and therefore the centrifugal forces applied to the gas. This next video shows an air compressor with inlet guide vanes and discharge diffuser vanes. Refrigeration compressors don't have the discharge turning vanes shown in the second half of the video. The first 40 seconds are all that apply to this lesson. Finally, compressors may be equipped with variable speed drives. The variable speed drives are more expensive, but also more efficient over the range of capacity. In many cases, the benefit of this control isn't worth the initial investment. Shown here are the performance of variable speed drives and inlet guide vanes. You can see at operating point D, the efficiency of inlet guide vanes is 88%, while the efficiency of a variable speed drive is 94%. In many cases, the cheaper inlet guide vanes will provide a better life cycle cost solution. As you can see at points F and G, both these control modes are limited in how low they can operate. At loads less than 40% for guide vanes and less than 60% for variable speed drives, the compressor is outside of its operating capacity. If the compressor needs to operate at points F and G, this can only be accomplished through the installation of hot gas bypass. In this lesson, we've focused primarily on the refrigeration cycle used in DX applications. The refrigeration cycle is also used in chillers as well as variable refrigerant flow systems, both of which are covered in dedicated lessons later in this course. But one or a number of the part load capacity controls presented in this last section are often used in these applications. The specific design and control sequences are often proprietary, but the fundamental technologies are relatively straightforward. Hopefully after this lesson, you have a better understanding of the inner workings of the refrigeration cycle and how it is used to defy Mother Nature and respond to varying loads. So if tonight, your spouse or friends ask you how your day was, be sure to dive right into the inner workings of the thermostatic expansion valve. It's a locked and loaded, 100% guaranteed conversation thriller. Just don't be surprised if they never ask you that question again. The objective for this lesson was for students to comprehend how the refrigeration cycle is controlled to provide cooling under various loading scenarios. The corresponding samples of behavior were: identify the four major components of the refrigeration cycle, identify refrigeration cycle process lines on the pressure enthalpy diagram, describe and explain the importance of superheat, outline how the thermostatic expansion valve uses differential pressure to control superheat, identify the controlled variable in various direct expansion applications, summarize the various part load capacity controls frequently used in the refrigeration cycle.